In this section, we're going to do some probability problems that we call OR problems and problems. Let's start with an example. We draw one card from a 52 card deck. We want to find the probability of drawing a queen or drawing a heart. So this is going to be what we call an OR problem. We want to find the probability of drawing a queen or a heart. Well, our first thought might be to find the probability of drawing a queen and add to that the probability of drawing a heart. Well, you'll notice that we have 4 queens in our deck, so the probability of drawing a queen is going to be 4 out of 52 total cards. Then, to find the probability of drawing a heart, we might notice that we have 13 possible hearts in our deck for a probability of 13 over 52. However, you'll notice from this diagram that when we counted our 4 queens and our 13 hearts, that we actually counted this queen of hearts twice. And since that queen of hearts only appears once in the deck, we've unfortunately double counted this card. To account for that, what we're going to do is we're going to subtract off the probability that we draw the queen of hearts. The way that we say that is we're going to subtract off the probability of drawing a queen and drawing a heart. Since there's just one queen of hearts in the deck, that probability is 1 over 52. And adding these numbers is going to give us the correct probability. They all have the same denominator of 52, so what we can do is we can just add 4 plus 13, subtract 1. I'm getting 16 over 52, which is a probability of approximately 0.308. Now this example leads us to a general formula. If we want to calculate the probability of event A or event B happening, what we can do is we can add up the probability of event A happening, the probability of event B happening, but what we have to do is subtract off the overlap of those two events. This formula might make a bit more sense if we look at a Venn diagram. The probability of A or B happening in this Venn diagram is given by this shaded region right here. Now the probability of A in this Venn diagram is given by this region. The probability of B happening in this Venn diagram is given by this region. But if we add those two probabilities up, we'll notice that we overlapped in this middle section. We counted this section twice. Well, this section in here is called the probability of A and B. So to correct for that overlap, what we do is we subtract off the probability of both A and B happening. So hopefully that Venn diagram makes this formula make a little bit of sense, because we're going to use this formula throughout the rest of this section. Okay, one more really quick note before we move on and do some more examples. If we have a Venn diagram that looks like this, where A and B don't have any overlap at all, then A and B are called mutually exclusive events. That just means that A and B can't happen at the same time. An example would be if A represented drawing an 8 from the deck, and B represented drawing a 5 from the deck. You can't draw both an 8 and a 5 out of a deck of cards, so those two events are mutually exclusive. Okay, let's use this new formula to do a couple of examples. We're given some probabilities, and we need to find a missing probability. If we just write down the formula from our previous discussion, we can plug in our known values. The probability of A is 0.6, the probability of B is 0.15, the probability of A and B is given to us as 0.1. That's going to allow us to find the probability of A or B happening just by adding and subtracting these numbers. When I plug that into my calculator, I get this result right here. The next example is another card selection problem. We want the probability of selecting a card below a 6 or a spade. Well, we can use this formula again, and I need to make a little bit of room. There, that's what we need to calculate to find this probability. Let's start with the probability that we draw a card that is valued below a 6. Let's scroll up and look at our list of cards. These are all of the cards whose values are below 6. It looks like there are 20 of them total. So I'm going to scroll back down to our problem. We have 20 possible cards that have a value below 6 out of 52 cards in the deck. So that's the probability for that piece. The probability of drawing a spade out of the deck would be 13 out of 52 because there are 13 spades in the deck. We need to subtract out the probability of a card being below 6 and a spade. So I'm going to go back up to our list of cards here. Which cards are below a value of 6 and spades? Well, these right here fall into both of those categories. So our overlap in this case between sets A and B includes those 5 cards. So I can come back down here and say that the probability of drawing a card below a 6 and a spade. Now again, all these fractions have the same denominator, so we can just add, and you could plug that into your calculator if you like, but I'm just going to leave it like that. How about another example where we're given some probabilities? We're going to use this formula again. and we're just going to plug in the numbers that are given. The probability of A happening is 0.3. We don't know what the probability of B occurring is. The probability of A and B happening is 0.1, and we're told that the probability of A or B happening is 0.7. What we end up with is an equation. On the left side is 0.7. On the right side, we have a 0.3 and a minus 0.1. Those can be combined or subtracted to give us 0.2, and we can solve this equation now for the probability of B happening. To do that, we would subtract 0.2 from both sides of the equation, leaving us with just the probability of B on the right side, and 0.7 minus 0.2 is 0.5, and we have answered the question. Okay, so far, all of the problems that we've done have been discussing situations where we're just running one experiment. But now we want to talk about probability problems where we're actually running two experiments. Maybe we're drawing two cards, or we are flipping a coin and then drawing a card. We're going to call these AND problems. I might prefer to call them AND then problems. Our notation is going to be similar to previous notation. We're going to be finding a probability of event A happening in the first experiment, and then event B happening in the second experiment. So you might think of these AND problems as having a then in here. And the rule for these probability problems is we can find the probability of event A happening in the first experiment, and we can multiply that by the probability of B happening in the next experiment. So here's an example. We're going to draw two cards from this very cute deck here, and we want to find the probability of selecting a card with a lion and then selecting a card with a red bird. We're going to do this both with replacement and without replacement. So the first thing that we want to do is find the probability that with our first selection we choose a card with a lion on it. So you can look at your deck of cards, and it looks like we have 5 cards with lions on them out of 20 cards total. That reduces to a probability of 1/4. Then what we're going to do is we're going to put that card right back in the deck because we're doing this experiment with replacement, and we want to find the probability of then selecting a card that has a red bird on it. So looking up at our cards, it looks like we have 3 red birds out of a total of 20 cards, giving us a probability of 3/20 for our second draw. Now, if we want to find the probability that with our first draw we choose a lion, and with our second draw we choose a red bird, we just need to multiply those two probabilities together. That's going to give us 1/4 times 3/20, or 3/80. You can plug that into your calculator and you get 0.0375, meaning we have a 3.75% chance of getting those two cards with those two draws. Now, we just did that problem with replacement. Let's try to do the same problem without replacement. Now, the probability of getting a lion with our first draw is going to stay exactly the same. However, this time we're going to leave that card out of the deck. We're not going to replace that card. And if we take that lion out of the deck, what that leaves us with is 3 red birds out of 19 possible cards. That slightly changes our probability for our second draw. And now, without replacement, the probability of drawing a lion with our first card and a red bird as our second card is going to come out to 3/76, and plugging that into my calculator gives me approximately 0.0395 as our probability. That's about a 3.95% chance of making those two draws. Now, when we draw two cards out of a deck with replacement, you'll notice that the probability of drawing a red bird was the exact same number that we would have gotten had we not drawn the lion card first. However, you'll notice that when we did these experiments without replacement, this probability right here changed based on the first card that we drew. In other words, this probability right here was dependent on what happened in our first experiment. Whereas this event and this event, when we ran the experiment with replacement, were totally independent of each other. In short, experiments run with replacement will result in independent events, but experiments run without replacement will result in dependent events. All right, let's look at this last example. We have 2 green envelopes, 4 red envelopes, and 3 blue envelopes. We're going to select one, find the probability that we select a green or a red envelope. Since we're just selecting one envelope, we're just doing one experiment here. So if we want to find the probability that that one envelope is either green or red, what we can do is add the number of green envelopes to the number of red envelopes. That is a total of 6 envelopes out of the 9 possible. That fraction reduces to 2/3, or you get 0.667. In the next problem, we select 2 envelopes without replacement. We're going to find the probability of selecting first a green envelope and then a red envelope. Notice that now we have 2 experiments, and we're not using replacement, so these are dependent events. What we can do is we can find the probability of selecting a green envelope and find the probability of then selecting a red envelope, Take those two probabilities and multiply them together. That'll give us our answer. Okay, so what is the probability of selecting that green envelope first? Well, we had 2 green envelopes out of 9 envelopes total. Now, once we've done that, what's the probability of selecting a red envelope? Well, it looks like we have 4 red envelopes left. Well, we've removed 1 green envelope and haven't replaced it. So that means that there were 8 total envelopes left. Multiplying these two fractions together gives us an 8 on top and a 72 on the bottom. You could reduce that to 1/9, or you could plug that into your calculator and get 0.111. In the next problem, again, we are selecting 2 different envelopes without replacement, and we're going to find the probability of selecting at least 1 green envelope. Now that has a key word in it. It says at least 1. And 2 sections ago, we came up with a probability formula that we could use for these at least 1 problems. The probability of an event happening at least once is 1 minus the probability that that event doesn't happen. So I think that we can use that here. In this example, this probability formula is going to read, the probability of selecting at least 1 green envelope equals 1 minus the probability of not selecting a green envelope with either of our selections. So with our first envelope selection, what is the probability of not getting a green envelope? Well, it looks like there are 7 envelopes that aren't green out of 9 total. Now that we've removed that envelope, what is the probability that with our second selection, we're also not going to get a green envelope? Well, we just removed one of the red or blue envelopes, so that means we have 6 envelopes left that aren't green out of a total of 8 envelopes. Well, I'm running out of room here, but I'm not going to forget my 1 minus. But multiplying these two fractions together gives us 42 over 72. Plugging that into my calculator gives me approximately 0.41667, or about a 41 to 42% chance that we will select at least 1 green envelope. Let's just do one more quick example. Again, we're going to select 2 envelopes without replacement, and we're going to find the probability of selecting 2 green envelopes. So we're going to find the probability of selecting green and then green. What is the probability that our first envelope is going to be green? Well, if I remember correctly, there were 2 green envelopes total out of 9 envelopes. So the probability that we select a green envelope with our first choice is 2 out of 9. And then once we've removed that green envelope from the pile, we have 1 green envelope left, and we'll have a total of 8 envelopes in that pile. So the probability of selecting a second green envelope is 1/8. Multiply those fractions to get 2/72. That reduces to 1/36, or you just plug it into your calculator, and you get 0.0278. So just under a 3% chance that you will select both green envelopes with your 2 selections without replacement. Okay, I think we're going to call this section there. Check out the homework assignment. Some of these problems mirror those homework problems pretty closely, so hopefully this is going to help you out. And send me emails if you have questions, and I'll see you guys in the next section.